In a previous unit, we had talked about ways to evaluate limits. And I had given you this list of kind of, these are the ways you want to try to evaluate limits in the order you want to try them in. First thing we always want to try is just substitution, because vast majority of limits we'll be able to evaluate that way. If that doesn't work, try algebraic simplification and then substitute again. We had talked about using a graph or table and sandwich theorem, but the one I put in the list and then put an asterisk by and said we'll have to come back to it is something called L'Hopital's Rule. And now's the chance for us to come back to it. And the reason for this is we had to learn our derivative shortcuts in order for this rule to be easy to use. One note is you may see L'Hopital spelled a little bit differently due to translation mistakes when his work, obviously French, was first translated into English. English translators originally translated his name incorrectly as this without the S, which you may sometimes still see it, but mathematicians right now are making a very concentrated effort to correct the spelling to show respect for L'Hopital's work in this area. But L'Hopital's rule is only sometimes going to be able to use. This is a rule that we have to use when we have limits that are in an indeterminate form. And I have this in two columns, here and here, because it kind of falls into two groups. The AP Calculus exam only focuses on these two, whereas these others I have further videos on because a lot of colleges you'll see those indeterminate forms. Please note that none of these are mathematically correct notations. They're just what we use for convenience sake to talk about which indeterminate form we're working with. But as we dive into examples, that will make more sense. But the basic idea of it is if I have a limit as x approaches a of some function over another function, and the result of that gives me an indeterminate form, such as, say, f is approaching 0 and g is approaching 0. If that's true, L'Hopital's rule says, well, we can go ahead and say this is going to be equivalent to the limit as x approaches a of the derivative of the top over the derivative of the bottom. This is very, very powerful, and actually the biggest issue is not that you're going to have trouble remembering how to do it. The biggest issue is you're going to want to do it every single time you see a limit that's of a quotient. The second mistake that comes up is this is not the quotient rule. We are not taking the derivative of the entire quotient. What we're actually comparing are the rates of change of the two functions. Because L'Hopital found that when both the top and bottom are approaching 0, or when the top and bottom are both approaching an infinity, either positive or negative, the ratio of their values that they're approaching is going to be equivalent to the ratio of their rates of change as you approach that x value. That's the key to what he did. But it's only in the very specific cases of your two functions that you're comparing are both approaching 0 or both approaching one of the infinities. So we're going to start with the 0 over 0 indeterminate form. Again, we don't ever actually want to write 0 over 0 like this. It's mathematically impossible to say that we're evaluating a limit that equals 0 over 0 and then suddenly equals a real number. But I'll talk through here with the examples how we actually go about notating this. So the first one that we're going to look at here is the limit as x approaches 0 of the sine of x over x, which we covered way back at the very beginning of limits. And we had done it graphically, and we know this equals 1. But we can also use L'Hopital's rule in case you happen to forget it. Because if I try substitution first, what I get is that the sine of x part is going towards 0, and the x in the bottom is also going towards 0. This is why we call it the 0 over 0 indeterminate form. But note, what I do is I show that the top approaches 0 and the bottom approaches 0. So because of this, we are allowed to apply L'Hopital's rule. If you are watching this video to help you prepare for the AP Calculus exam, you do have to indicate that you are using L'Hopital's rule in some way. So using an arrow is the safest bet. And then you can put L'(H) for L'Hopital. You can put just LH. You can write out L'Hopital. But you have to somehow indicate that the limit that we're evaluating, we're applying L'Hopital's rule to in order to get an equivalent limit. So when I apply L'Hopital's rule, I haven't found the limit yet, so I still need the limit as x approaches 0. I'm still going to have a quotient, but because this is L'Hopital's rule, it's no longer a quotient that we're thinking of. It's actually a ratio where we're comparing sine of x to x. And L'Hopital says that the rate of change for sine of x is going to, compared to the rate of change of x, will be equivalent to the rate of change of the derivative of, I have to start that over. Will be equivalent, when I compare the values of sine of x to x, that's going to be equivalent to comparing the rate of change of sine of x, which we know is cosine of x, to the rate of change of x, which we know is 1. Remember, rate of change means derivative. And so I have an equivalent limit now, and I try substitution again. When I plug 0 in, I get 1 over 1. And here is our answer. Incredibly powerful, because if we have one of our indeterminate forms, the top approaches 0, the bottom approaches 0, or the top approaches positive or negative infinity, bottom approaches positive or negative infinity, then we are able to look at the comparison of the derivative of the top to the derivative of the bottom and try substitution again. So if I go to the second example here, the limit as x approaches 0 of the square root of the quantity 1 plus x minus 1 all over x. First thing I would try is substitution. When I plug 0 in for x, my top is approaching 0. The bottom is quite obviously approaching 0. So I'm able to apply L'Hopital's rule. So I'm going to indicate that I'm using L'Hopital's rule. And what I now have is a new limit as x is approaching 0, because I haven't evaluated it yet. Remember, square roots are not very friendly to us, so if I think of this as 1 plus x raised to the 1/2, I need the derivative of that. Remember to watch your chain rule there, so derivative of the outside times derivative of the inside, which is just 1, minus the derivative of 1, which is 0, all over the derivative of x, which is 1. And I'm going to try to go ahead and do substitution again now. So if I plug 0 in for x, I get 1 to the negative 1/2, which is just going to be 1 times 1/2, which gives me 1/2. And there's our derivative. If I keep going with this, I can go and do even further examples. So if I look at the limit as x approaches 0 for the square root of 1 plus x minus 1 minus x over 2 all over x squared, again, the first thing I would try would be to plug 0 in. So that's 1 minus 1 is 0 minus 0. So my top is going to 0. My bottom is going to 0, which means I am able to apply L'Hopital's rule. I haven't found the limit yet, so I do still need the notation. Limit as x approaches 0. Derivative of my bottom is 2x. Derivative of the top, I already found this derivative in our previous example, so I know it's 1/2 times 1 plus x to the negative 1/2 minus 0, and then x over 2 is the same as 1/2 x, so minus 1/2. Well, if I try going ahead and doing substitution again, plugging in 0, this becomes 1/2 minus 1/2, so my top is going to 0. And my denominator is going to 0. So this becomes an issue again, but it's not a big deal because L'Hopital's rule is actually a very strong formula in that this still falls under, it's a limit where the top is going to 0, the bottom is going to 0. I can do the derivatives again. So if I do the derivatives again, this means I can apply L'Hopital's rule a second time. And as long as we have one of our indeterminate forms, we can keep doing L'Hopital's rule until we get an answer or we get to a point where we can show this does not exist. I still haven't evaluated the limit yet, so I still have the limit notation. For the derivative of the top, I now have negative 1/4 plus x raised to the negative 3/2 minus derivative of 1/2 is 0. On the bottom, I have 2. And if I try to do substitution again, I get 1 times negative 1/4. That's negative 1/4 divided by 2 is negative 1/8. And there is our answer. One thing to watch for is you have to make sure it's an indeterminate form to use it. So some quick examples of this. If I look at this limit here, the limit as x approaches 0 from the right of sine of x over x squared. If I try substitution, I have top and bottom both approach 0. So I can apply L'Hopital's rule. I have the limit as x approaches 0 from the right of the cosine of x over 2x. Now when I try to plug in and 0 for x and do substitution, I have 1 over 0. Now what a lot of students will struggle with here is they'll look at this and they'll say, oh, I'm going to go ahead and do L'Hopital's rule again. But we can't. While the denominator is approaching the value that we want for L'Hopital's rule, the numerator is not. And what this means is when we reach this point where one of the derivatives approaches 0 and the other doesn't, then our limit is going to equal 0 if it's the numerator that approaches 0, or it's going to be positive or negative infinity if the denominator approaches 0. So if I look at this example here, this is going to be one of my infinities. To decide which one, I can actually just say, well, x is going to be a small, since I'm approaching from the right, x is a small positive number. So my denominator is going to be positive. And because it's a small positive number on the unit circle, it would be in quadrant 1. So the cosine of x will also be positive. So this is approaching positive infinity. Hopefully this is helpful. If you try out the second limit there on your own, you should get that the second limit is approaching positive infinity. Or, I'm sorry. The second limit should be approaching negative infinity, I believe.